Hi everyone. In this video, we are going to talk about software connectors. This is a really important lecture. So we will look into different software connectors, in software architecture and design space. So what are connectors? In simple terms, connectors are the pathways through which components of a system communicate. They define how information flows between different elements of the system. Imagine you are working on a group project. To make sure everyone is on the same page, you need to communicate with each other. You could send emails, use chat apps, or even meet in person. The way you choose to communicate is like a connector in the software system. So, same processes. There are different ways you can use connectors. Same processes like local communication. If two parts of the software are in the same environment, like two teammates sitting together, they can simply talk directly with each other. This is like calling a function within the same program, where one part gives the other some information and gets a response back immediately. Examples: if a calculator app has both an addition and a subtraction module in the same process, they just call each other's methods directly. That's an example of same process. Now, different processes on the same computer. If two parts are on the same computer but running separately, like two people working from the same office but is in different rooms, they may not directly talk but can leave messages to each other. This could be done using message queues or pipes, which are like digital sticky notes passed between them. An example is an email client and an email server, both on the same computer, might pass messages to each other through a queue, ensuring the email is stored and forwarded as needed. Fine. And then there are different computers or remote communication. Now, what if your system has two parts that are far away from each other, like two teammates in different countries? They will need to use something like a video call or chat app to exchange information. In software, this could be done through remote method invocation or RMI, or web service calls, which allow different systems to talk across the internet. Example, in a banking system, if your mobile app on your phone needs to interact with the remote server for balance checking, it will send a request to the server and get the information back through a web service call. As the system design evolves, the connectors are refined based on where different components live in the system. During the design phase, if two elements stay in the same processes, use local methods. If they are in separate processes in the same machine, use message queues or pipes. If they are different machines, use remote method calls or web services. Software connectors can be classified in various ways, such as synchronization mode, how communication happens, initiator, like who starts the communication, implementation type, like how it's built, active time span, like when it's active, fan out, that means how many components it interacts with, information carrier, what kind of data it passes, or environment, like where it's used. For today, we are focusing on the synchronization mode of connectors. This means how the connectors behaves when one part of the system sends a request to another part. There are two ways: blocking versus non-blocking connectors. Blocking connectors and non-blocking connectors. These are the two main types of connectors based on synchronization mode. Uh, let's break them down. The blocking connector is like making a phone call. When you call someone, you wait on the line until they pick up an answer. You can't do anything else during that time. In software terms, one part of the system sends request to another part. This is a method call or a message, and then waits for a response before moving on. The component can't do anything else while it's waiting. Example, imagine a shopping website where you place an order. The system makes a request to check if the product is in stock. While waiting for a response, whether the product is available, the system can't process anything else. And there is non-blocking connectors. A non-blocking connector is like sending a text message. You send the message, and then instead of waiting for a reply, you go on with your day. When the other person responds, you will get the message, but you are not stuck waiting for it. In software terms, one component sends a request to another but doesn't wait for a response. It can continue with other tasks while the response is processed in the background. Um, for example, in the same shopping website scenario, if after you place your order, the system immediately confirms the order and continues processing other requests. The check for stock availability happens in the background. So understanding whether a connector is blocking or non-blocking is crucial for designing efficient systems. Blocking connectors are simple but may slow down your system because the parts of your program are sitting idle waiting for a response. While non-blocking connectors can make your system faster by allowing parts of your program to multitask, handling multiple things at once. So what is an initiator? Now let's talk about connector initiator classification. An initiator is like the person who makes the first move in a conversation. In software system, the initiator is the part of the system, an element that sends a request through the connector to another part of the system. So this is basically the first person sending a text message. Two types of initiators there are. One is depending on who make the request, connectors are classified in two categories: one initiator connectors and two initiator connectors. So a one initiator connector is like a teacher giving instructions to students. The teacher, that is the initiator, can tell the student what to do, but the students can't tell the teacher what to do in return. In software world, only one part of the system, the initiator, can send requests to the other part. The second part cannot initiate communication. For example, think of an ATM machine and a bank server. The ATM here is the initiator, sends a request to the bank server to check the balance or process a withdrawal. But the bank server doesn't send requests back to the ATM. In this case, only ATM sends requests to the bank server. The communication is one directional. A two initiator connector is like a conversation between two friends. Either friend can start talking and ask questions. There is no restriction on who can initiate the conversation. In software, both part of the system can send requests to each other. This type of connector is essential for callback functionality, where one part can send a request and the other part can also send a request back. Example, in a video call app, both participants can initiate communication. One user can call the other, and during a conversation, the other user can also send messages, share screens, etc. Here, both users can initiate communication with each other, allowing for two-way interaction. The type of initiator your system uses defines the flexibility and directionality of communication. One initiator connectors are simple and useful when communication only needs to flow in one direction, like a client-server model. Two initiator connections or connectors allow two-way communication, which is necessary when both parts need to interact, like in real-time systems or apps with callbacks. Imagine connectors as highways between two parts of a system. Information flows through these connectors like cars traveling on the highway. However, the method of transport or how the transformation information is carried can differ based on the relationship between the elements connected. Now let's explore some how information carriers work in different scenarios. Scenario one, same process, two threads. If the two parts of the system called incident elements are running in the same process, like two threads in the same program, the simplest way for them to share information is by using a shared variable. Example, think of two workers in the same room sharing a notepad. They can write information on the same notepad and can read what the other person has written. In this case, both thread 1 and thread 2 can access and modify the same data, just like sharing a notepad. Scenario 2, different processes, same processor. When the two elements are in the different processes but running on the same processor, the communication gets a bit more complex. Since they don't share memory, they need other resources like pipes, files, or local message queues to exchange information. For example, this is like two workers in the separate rooms using a pneumatic tube system to send documents back and forth. They can just share the same notepad, so they pass messages through the tubes. Finally, scenario 3, method invocation and message passing. In many systems, instead of relying on shared variables or files, communication between parts of a system is more structured through a method invocation or message passing. Method invocation is like one element calls a function or method in another element and waits for a response, just like a phone call. And message passing is one element sends a message to another and the receiver processes it whenever it is ready, similar to sending a letter or text message. Imagine a web application where the user clicks on a button and then the app sends a message to the server to fetch data. The server processes the request and sends back the data. In this case, for example, if it's a get user data, this method invokes a database request while send message passes the message to another part of the system for processing. Choosing the right information carrier is important because shared variables are fast but can only be used when elements are in the same process. Pipes, files, or queues are useful for separate processes that needs to exchange data but live on the same environment. Method invocation and message passing offer more flexibility and structure, especially in distributed systems. In many systems, the elements we want to connect might not even be on the same machine. For example, think of an online shopping app where you are on your phone and the backend server is far away in a data center. To communicate, we need special mechanisms like remote method invocation or RMI or messaging system. So what is an RMI? RMI allows one part of the system to call a method in another part, even if that part is running on a completely different computer or processor. This is like making a long distance phone call. You are asking a remote server to do something for you and send back the results. A messaging system is slightly different. Instead of directly calling a method, one part of the system sends a message to another part. The message goes through a network, like how a letter goes through a postal service, and a receiver picks up the message and processes it. Example is, let's say subsystem 1 wants to send a data to subsystem 2. It uses a message sender module to send the message. And subsystem 2 uses the message receiver module to get it. The two systems communicate over a network, but before they can understand each other, they must agree on a message format and a protocol. Think of this like two people who speak different languages but have to communicate. They first agree on a common language, like the message format, and rules for how the conversation should go, like the protocol. Uh, in your slides figure, there is a message system connecting subsystem 1 and subsystem 2. The message system has two key parts: message sender module, part of subsystem 1, and message receiver module, that is part of subsystem 2. These two modules communicate over a network. They both need to agree on the following. Number one is message format. This defines how the message is structured. For example, it could be a JSON object or an XML file. Protocol is the rule of conversation. It includes how messages are sent, what happens if something goes wrong, and how the receiver knows when it has received the full message. Let's say subsystem 1 wants to send a user order details to subsystem 2. The message might be structured like a JSON. So JSON can have order ID 1, 2, 3, 4, 5, and product is laptop, and how many quantity that is 1. Both subsystem 1 and subsystem 2 must understand this format so they can properly set and receive messages. The protocol might include things like subsystem 1 sends a ready signal before sending a message. Subsystem 2 sends an acknowledgement once it receives the message. If subsystem 2 doesn't acknowledge, subsystem 1 retries after a certain amount of time. This ensures the two systems can communicate smoothly, even if there are delays or interruptions in the network. In this diagram, you'll see two small circles. I think no. In this diagram, yes, there are two small circles. Over here, one circle, and over here, another circle. On the arrows connecting the message system to the two subsystems. These circles represents the interface that connect the message system to the elements. Interface 1 connects to subsystem 1 to the message system sender module. Interface 2 connects subsystem 2 to the message system's receiver module. These interfaces define how two subsystems talk to the messaging system, making sure the communication is seamless and understandable. When we talk about implementation type of a connector, we are referring to how the connector is set up to manage communication between two parts of a system. Let's start with the first type, signature-based connectors. A signature-based connector is like a very specific set of instructions where each part of the communication knows exactly what operation is going to happen. The method name represents the operation, and the parameter represents the data or arguments needed for that operation. Imagine you're ordering a pizza over the phone. The operation is clearly defined by the method name order pizza. And the parameters are the details like the size of the pizza, the toppings that you want on the pizza, and the delivery address. In a signature-based connector, the operation is fixed. The method does one thing. It orders a pizza. If you wanted to order something else like a drink, you would need to define a new method. One neat feature is that you can modify the method to handle different operations based on parameters. For example, if we want to allow the method to handle multiple order types, we could modify the parameters list. For example, if we have a method named place order with order type and details, if order type equals to pizza, then ordering a pizza with details, and if the order type is drink, we are ordering drinks. This makes the connector a bit more flexible by using parameters to indicate operation type, but the overall method still quite rigid in its purpose. And then we have protocol-based connectors. These are more flexible. Instead of having a method for every specific operation, a protocol-based connector supports multiple operation types through a single binding signature. The key idea is that protocols define how the communication happens, and the system can extend to support new operations even after the interfaces are defined. For example, let's go back to our pizza order. Imagine that instead of calling a person directly, you use an online chatbot to order. The chatbot doesn't just handle pizza orders, it can take many kinds of requests, like tracking an order or providing help. The chatbot knows how to handle different types of requests because of the protocol that governs the conversation. The operation in signature-based connectors, the operation is fixed. The method name represents a specific action, and the parameters are tied to that action. It's simple but less flexible. In protocol-based connectors, the operation is fixed. The method, the system can handle multiple operations through a single interface. New operations can be added without modifying the interface, making it much more flexible for growing subsystems or growing systems. Now let's talk about connector active time classification. A program connector active time refers to when an operation request message is sent over a connector. Connectors may be classified into program connectors and event-driven connectors. A program connector is the most straightforward type of connector. Here, a method call is programmed to occur at a specific point in time. When the execution reaches a certain line of code, the method is called. Example, think of a train schedule. The train leaves the station at a specified time. If you arrive early or late, you have to wait until the scheduled departure time. In programming, this is just like calling a method from another method. Once the code reaches that specific line, the method gets triggered. Programmed connectors are common in traditional systems where you have specific steps that need to be followed in a sequence, such as in business processes, data processing, or mathematical calculations. Now let's talk about event-driven connectors. An event-driven connector, on the other hand, is more flexible. In this case, a method call or message isn't triggered by a specific line of code, but an event that happens in the system. This is like reacting to something unexpected or outside of regular flow of operations. An event can be anything: a user clicking on a button, a sensor detecting a change, or a message being received by another part of the system. Imagine you are at a bus stop, but the bus doesn't leave until the passengers press on Depart Now button. The bus leaves whenever the button is pressed, which is triggered by an event, that is the press of the button, rather than at a scheduled time. Systems, real-time systems like systems that uses alarm systems or air traffic control systems need to react immediately to events, like a sensor being triggered or an aeroplane entering a restricted zone. So this is an event-driven connector example. Another example is graphical user interfaces or GUIs. In any system with a graphical user interface, such as websites or mobile apps, actions like button click or text input are event driven. For instance, you click submit button on a website. The submission system only performs the action after the event occurs or the click occurs. So the key difference between program connectors and event-driven connectors: the program connector, this method is triggered at a specific point in the code, like a train running on a schedule. It is predictable, happens at a fixed time, and is sequential. Event-driven connectors, here the method triggered by an event like a button press or a new message notification. It is flexible, reactive, and allows system to respond in real-world scenarios or real-world events. Connector span. The span of a connector refers to how far apart the elements are that it connects. Here they close together operating on the same processor, or are they far apart, possibly on different machines across a network? The connector span always plays a crucial role in deciding how to implement the connector. A local connector is used when both incident elements, these parts of the system that communicate, are located on the same processor. This means that communication happens within a single machine or system, often within the same process or application. Think of two workers sitting in the same office. When they need to talk to each other, they don't need to use email or phone calls. They just can speak directly. The connection between them is local, so communication is fast and direct. In programming, local connectors are often implemented using method calls or shared memory. These connectors are fast because there's no need to go through a network or other external systems. A network connector is when the incident elements are located on different machines or processors. These elements communicate over a network, such as the internet or a local area network or LAN. Network connectors are often more complex because they have to deal with the challenges of distributed systems like latency and reliability. Imagine two co-workers from different offices in different cities. They just can't directly talk to each other. They need to use email, phone calls, or video conferences. This communication method goes through a network, making the connection remote. In programming, network connectors are commonly implemented using RMI, that is remote method invocation, web services, or proxy design pattern. In distributed systems, one common way to implement network connectors is by using a proxy design pattern. The proxy acts like a local representative for an object located in another machine. When a local element calls a method on the proxy forwards the request over the network to the real object located remotely. Um, So the key difference between local connectors and network connectors, when the incident elements are on the same processors, local connectors allow for fast and direct communication using method calls or shared memory. They are simple and efficient, but limited to systems within the same machine. Um, Network connectors, these are used when the incident elements are on different machines. They rely on network communication. They are often implemented using the proxy design pattern or other distributed communication techniques. Network connectors are slower than local connectors due to the network overhead, but they enable remote interaction. So let's look at some real world applications. Local connectors are ideal for systems where all components are housed in the same server or in the same application, such as a desktop application or an embedded systems, that is robotics or IoT devices. Network connectors are essential for systems like cloud-based applications, web services, or microservice architecture, where components are distributed across multiple servers or locations. Imagine we have two subsystems. The initiator located on one machine on the process, that is subsystem 1, and the subsystem 2, the receiver located on a different machine or process and is exposed an interface that subsystem 1 can call. Since subsystem 1 and subsystem 2 are located on different processors, a network connector is required for communication. But how does subsystem 1 invoke a method in subsystem 2? As if subsystem 2 were right there in the same process. That's where proxy and skeleton objects come in. In distributed systems, when you want one subsystem to interact with another subsystem over a network, you can't just directly call methods like you would in local connectors. Instead, a proxy and skeleton are generated to simulate that interaction. The proxy object is located in the same process as subsystem 1. It exposes the same interface as subsystem 2. This means subsystem 1 interacts with the proxy as if it's interacting with subsystem 2. The proxy object gives subsystem 1 the illusion that subsystem 2 is local, even though it is remote. The skeleton object resides in the process where subsystem 2 is deployed. It receives a method call forwarded by the proxy and translates it into something subsystem 2 can understand. The skeleton processes the request, interacts with subsystem 2, and returns the results back to subsystem 1 through network. The proxy and skeleton communicate over the message system, passing method calls and returns values subsystem 1 and subsystem 2. These proxy and skeleton objects aren't manually coded. They are usually generated by tools specific to technology being used. For example, in Java RMI, Java generates the stub proxy and skeleton objects automatically from remote instances. In web services, tools like WSDL, that is Web Service Description Language, generate the proxies that allow clients to interact with remote services as if they were local. So what are the benefits of using proxy and skeleton objects? Number one is abstraction. The proxy provides a local abstraction for remote services, hiding the complexity of network communication. Number two is transparency. Subsystem 1 can invoke methods on subsystem 2 as if they are located in the same process, even though it's deployed on different machines. And finally, scalability. This design pattern makes it easier to scale distributed systems by keeping the communication seamless for the initiator. Now let's look at connector fan-out classification. What is fan-out? Fan-out is a connector defines how many other elements a single element can connect. For example, is it only talking to one of other element, that is one-on-one, or can it talk to multiple elements, that is one to many in the same time? The attribute has a major impact on how connectors is implemented and how it is performed. A one-on-one connector is used to connect exactly two elements. In this case, a connection is exclusive between these two elements and no other element can join this communication. For example, think of a direct phone call between two people. The conversation is private and no other people are involved in the call. In software system, this kind of connector is useful when two elements have a dedicated relationship, like a database connecting to a specific application. The connection is only between the application and the database. Now let's look into one-to-many connectors, that is one-to-many. A one-to-many connector allows one element to connect to many other elements in the same type, that is like a broadcast or a server-client relationship, where the single server can serve multiple clients simultaneously. Think of a web server serving multiple web browsers at the same time. The server is one element and it can handle requests from many clients like web browsers, all connected at the same time. In software system, one-to-many connectors are common in client-server architecture where a single server handles many clients. For example, a web server can serve many web browsers or database server can handle requests from multiple applications. The fan-out attribute significantly impacts both implementation and performance. One-on-one connectors are generally simpler to implement and manage since they only need to handle communication between two elements. Performance is often predictable as there is no connection for resources or competition for resources. For one-to-many connectors need to handle many connections simultaneously, which adds complexity. For example, a web server serving multiple clients must manage multiple requests, balance resources, and ensure that no single client affects the performance for others. The environment of a connector refers to the context in which the connected elements operate. Are they using the same technological stack or different technologies? Based on this, connectors can be classified in two main types: homogeneous connectors and heterogeneous connectors. Homogeneous connectors are used when the elements being connected are in the similar environment. This means that both elements are implemented using the same programming language, use the same software framework, run on the same operating system. Because everything is similar, communicates between the two elements is often simpler. For example, think of two co-workers using the same tools and languages to communicate. They work in the same office, they use the same software, they speak the same language. This makes the communication fast and easy without the need for translation or extra steps. In software, homogeneous connectors are common in systems where all components are developed with a unified technology stack. On the other hand, heterogeneous connectors are used when connected elements are in different environments. This means that elements may be implemented using different programming languages, use different software frameworks, run on different operating systems. Because of these differences, heterogeneous connectors are more complex and often requires translation layer or brokers to facilitate communication between the two elements. Imagine two workers who speak different languages and use different software tools. They can't communicate directly, so they use an interpreter or a broker to help them understand each other. This is what happens in heterogeneous systems. This is a broker or message system that helps different technologies work together. In software, this might be a Python service interacting with a Java service on different operating systems. These elements communicate over the network using standards like CORBA, that is CORBA, or web services. Heterogeneous connectors and the broker design pattern. One common pattern is used in heterogeneous environment is the broker design pattern. In this pattern, the broker acts as an intermediary between different components. The message system allows for communication between message sender and message receiver. The sender and receiver may be implemented in different programming languages or run on different operating systems. Think of a web service where a Python client calls a Java-based web server. The broker could be a REST API or a web service that handles the requests and responses between the Python client and Java server. This approach ensures that systems developed in different languages and environments can still communicate seamlessly. Uh, for example, Common Object Request Broker Architecture, or CORBA, allows objects written in different languages and running on different platforms to communicate. It abstracts away complexities of different languages and operating systems, providing a standard way to communicate heterogeneous systems. Another example is web service. There are two popular web services, that is SOAP, Simple Object Access Protocol, and REST, Representational State Transfer, are common standards for enabling communication between different systems, often implemented using either JSON or XML. So the key difference between homogeneous connector and heterogeneous connector is homogeneous connectors use same language, framework, and operating system, simpler to implement and often more efficient since there's no need to translation between technologies, typically used in monolithic or tightly coupled systems. Heterogeneous connectors are use different languages, frameworks, or operating system, more complex to implement as you need a broker or middleware to handle communication, common in distributed systems where components are developed independently using different technologies. So let's quickly look over the broker design pattern. In this scenario, two subsystems are implemented in different programming languages and run on different platforms, but they communicate seamlessly using the broker design pattern. The key components here is proxy object lives in subsystem 1 and is written in the same language as subsystem 1. It marshals or converts data into a platform or language independent format and sends it to the skeleton object over the network. The network has skeleton object. It lives with the subsystem 2 and is written in the same language as subsystem 2. It receives the marshaled data, unmarshals it into the subsystem 2's format, processes the request, and sends the return value back to the marshal form. The application level protocol ensures that the operations and arguments are represented in a language independent way, allowing the two subsystems to communicate. The communication flow is as follows. Subsystem 1 calls a method on the proxy. The proxy marshals the data and sends it to the skeleton. The skeleton unmarshals it, processes the request, and sends it back the return value. The proxy then unmarshals the return value and gives it to subsystem 1. This approach allows two systems written in different languages and running on different platforms to communicate effectively by using the broker, ensuring data transmission and platform compatibility. In our next video, we will talk about an agile approach to software architecture and design.